Hi guys, Ms. Peterson here, and welcome to our chemistry lecture on nuclear decay. In this lecture, we're going to be going over alpha, beta, positron emission, and gamma decay, as well as how we use half-lives to determine the age of radioactive samples. So let's go ahead and get to it. First off, quick review. When we work with nuclear decay, we're going to be dealing with changes in the nucleus, so we will be writing stuff in isotope notation. So in isotope notation, you got the symbol of the element, okay? In that middle one, the atomic number, the identity of the element is there, so the symbol and the atomic number will always go together. And then you have the mass number, and that one is the one that's specific to the isotope, okay? Carbon always has 12 protons, so if you have a 12 there, it's always going to be carbon. But carbon can have 6 protons and be carbon 12, or 7 protons and be carbon 13, or 8 protons and be carbon 14. So the mass number can be different. So what is radioactivity? Okay, so all radioactivity means is that an atom will spontaneously emit radiation. Now, these atoms that emit radiation are called radioisotopes. Okay, they are unstable, so they decay into more stable atoms. And because they decay, they're typically not the most stable isotope of that element, and not the most common because, they decay. Now, we tend to think of radioactive as always meaning bad, but we use radioactivity in smoke detectors, in nuclear reactors. We use it to track how medications move through the body, tons of medical applications. We use it to date our rocks and our fossils, and a lot more. So how do these atoms decay? Well, there are 4 main types. The first is alpha radiation. Alpha radiation is when the atom emits an alpha particle, aka helium nucleus. Now this one has the symbol 42He if you're talking about it in terms of the alpha particle, or you might see it as the alpha, okay, the Greek letter. Now there's also beta decay. Beta decay happens when inside the nucleus, a neutron changes into a proton. So since a neutron is neutral, in order to become positive, it has to get rid of its negative charge. So the electron gets emitted and that neutron changes into a proton. Now, since it's an electron, it has very little mass, but a charge of -1. And now it's like you've gained a proton. So this is kind of like -1 proton that's leaving the atom, okay, so that there could be 1 proton left. And you might see it with an E, or sometimes you will see it with the B for beta, okay? That's beta minus decay, and just like neutrons can change into protons, protons can change into neutrons. And when that happens, it's called positron emission. Now, for a proton, a positively charged thing to change into a neutron has to get rid of its positive charge. Now, it emits a positron. Now, a positron is the antiparticle of an electron, so sometimes the notation is similar with the mass of 0, but the charge of +1 instead of -1. But again, sometimes you will also see it with the beta particle. Okay, cool. Now, the last type of radioactive decay is gamma decay. This happens when it just emits a light ray, okay, light radiation. This happens when the electrons move from their excited states to their ground states. It's denoted with a gamma, and it doesn't have any mass. It's not a proton or an electron, so no charge or anything like that. So normally you'll see it as the Y, sometimes with the 00, or sometimes just the Y. Okay. So those are our 3 basic types. In alpha decay, we have the nucleus emitting a helium, so that the daughter nucleus is going to be -2 protons and -2 electrons. In beta minus decay, it emits that negative charge, so the daughter nucleus will be +1 proton and -1 neutron. And in gamma decay, it just emits light, so there isn't really a big change to the nucleus. Okay, let's go ahead and see how we write these. Oh, before we get to that though, I have a quick chart here with the shortcuts. You have the symbol. I would add the beta particle, the 0, -1e, to that one. But you can see that mass of 4, 1 over 118,000, so approximately 0, and gamma is 0. This also gets to how strong and damaging these types of radiation can be. Alpha radiation can be pretty damaging, but it can be stopped by things like your clothes, a sheet of paper, okay? It just doesn't go very far. The ones coming off of our smoke detectors in our room right now are traveling just a couple inches before they decay. For beta particle, it can get through like skin a little bit. It can be blocked by a sheet of like metal foil. Where gamma radiation, that's the stuff that like the x-ray technician has to go in the other room because they don't want to get that all day, every day. A couple dose of x-rays for you won't be bad, but they put the big lead brick over to protect your internal organs. And again, that's just because gamma radiation can cause damage to your cells by causing it to the atoms to emit electrons. But it's blocked by not blocked by our magnetics. Our gamma radiation is blocked by our magnetic field around Earth. So much of the gamma radiation coming from space and stars and things like that doesn't reach us, and there's not very many processes here on Earth that produce that kind of radiation in large amounts. Okay, so the skill we need is to be able to write these. Okay. And the name of the game here is just to follow the law of conservation of matter. Okay, and to just makes sense because that's what's happening. We have our uranium nucleus here. That is uranium with a mass of 235. It's uranium, which is number 92 on the periodic table. So it's always going to be a 92 in that lower corner. Now it decays via alpha decay, where it emits the alpha particle, which has 2 protons and 2 neutrons. Okay. Now, if the nucleus emitted that alpha particle, it lost 2 protons. So it only has 90 left in the daughter nucleus. Okay. For the mass, it had 235. You can think of the arrows as your equals. It lost 4. So we just have 231. Okay. Now, to figure out what symbol goes there, we go by the atomic number, the identity of the element. And we look on our periodic table and we find number 90. And it is thorium. Okay. So thorium goes there. And, it was also written right there. Yep. So if we're looking back at this to understand what's going on here, we have 92 equals 2 plus 90. Okay. 235, it decayed into one particle that had 4, one particle that had 231, because 231 plus 4 equals 235. Okay. Now, beta decay can be a little bit more complicated, so let's look at that one. Now, in beta decay, we're going to do a beta minus and a beta positive. So carbon 14 undergoes beta minus decay. And this is actually how we date fossils, okay? So when it decays, it emits that electron with no mass and that -1, okay? So that happens when a neutron changes into a proton. So the number of protons is going to go up by 1. Instead of having 6, now it has 7. But the mass doesn't change because neutrons and protons have approximately the same mass. So that'll be 14. We look at number 7 on the periodic table, and it is nitrogen. Okay. And this also checks out because 7 plus -1 equals 6. Okay. -1 plus 7 equals 6. 14 equals 0 plus 14. Okay. Cool. Also, just a note, it doesn't matter what order you write the electron and the nitrogen atom. You can write them in any order, just as long as the arrow's in the right place. Okay. So let's go ahead and try the beta plus decay. Carbon 10 undergoes beta plus decay. So it's still carbon, so it's still atomic number 6, but now it's going to emit the positron, which is 0, 1, And I like to use the beta particle for the positron. The E feels funny to me. But then again, in the physicsclassroom.com concept builder that we'll do on this, which is excellent, I highly recommend. I'll link it in the description. They use the E, so maybe I'll use the E. So that happens when a proton changes into a neutron. So the number of protons is going to go down by 1 and be 5. And the mass doesn't change. Number 5 on the periodic table is boron. Yep. And again, it still follows that law of conservation of mass. 6 equals 1 plus 5. 5 plus 1 equals 6. 10 equals 0 plus 10. Okay, cool. Okay, cool. So last thing we're going to talk about is half-life. Okay, half-life is how these radioactive isotopes and these decay reactions are actually used to learn things about the world, like how long ago the dinosaurs lived, or how old the moon is, or how long ago this mummy died. Okay, so what a half-life is it's defined as the amount of time that it takes for 50% of a radioisotope to decay. Now, this is a probability thing. We modeled it with the M&Ms in the cup, shaking them and spinning out. And if they're M side up, they are not decayed. If they're M side down, they have decayed. Okay. That will always be a 50% ratio. So it's not going to be a linear, like 10 atoms decay every hour. Instead, it's going to be a percentage, 50% decay every half-life. So after one half-life, you are at 50% of parent atoms. So you'll have 50% of your parent atoms and 50% your daughter atoms. If you're only halfway to that half-life, you would still have 75% of your parent atom. Now at 2 half-lives, you'll be at only 25% of your parent remaining. 75% of it will be daughter atoms. Okay, 3 half-lives, okay, 12.5%, 4 half-lives, 6.5, etc., going down by half every time. Now, different elements have different half-lives, and this allows us to date a variety of ranges. So let's see how we use those in an example problem. But before that, some common radioisotopes. You can see the naturally occurring ones like carbon-14. It has a half-life of about 57,000 years, so for more recently dead things. Where for potassium and uranium, those have half-lives on the order of 1 billion years. So we can use them to date really, really old rocks and things. Okay? Where more recent thus, things maybe we'll use its strontium isotopes, okay? Which have a half-life of 38.1 years. And then these are some common medical ones. We use a lot for tracing medication in the body and things like that. Okay, cool. So carbon-14, used to date fossils, has a half-life of 5,730 years. A certain fossil was found where there were 25 grams of carbon-14 remaining and 75 grams of nitrogen-14, the decay product of carbon-14. All right, so we're talking about a carbon atom here decaying into the nitrogen atom. So we know that it's going to be a beta decay, where the carbon-14 is going to be our parent atom, and the nitrogen-14 is going to be our daughter atom. Okay. Now, when we do these types of decay reactions, we are going to use the table method. Okay. Now, there is an equation you can use, but it uses natural logs and exponents and things like that. So for the purposes of our class, normally it's going to be easier to just use a table. So I'm going to have the amount of, or the half-lives, the time that it's been, and then our amount remaining. So we need to think about our sample. Our sample had 25 grams and 75 grams. So we know we started with a total of 100 grams at 0 half-lives, okay? So 100 grams of our parent atoms of our original undecayed sample and 0 grams of our decay product. Now, 1 half-life is 5,730 years. Now, after that, 50% of it will have decayed. So if we had 100 grams to start with and 50% of it decayed, we'll have 50 grams of our carbon-14 and 50 grams of our nitrogen-14. Okay? Now, after 2 half-lives, Okay, that's 5,730 years times 2. 5,730 years times 2. 11,460 years. Now, half of this carbon-14 will have decayed. So we'll be down to 25 grams, which means we'll have 75 grams of our nitrogen-14. Oh, and hey, that was what we were looking for in the problem. So we can go ahead and stop there because our answer is 2 half-lives or 11,460 years. Okay. And then just for fun, so you guys can see how this would work, if we went on to like 3 half-lives, oops, don't want to be on highlighter. 3 half-lives, we would add another 5,730 years. Have that many years, and we would be down to 25 divided by 2 is 12.5, which would get added to this one. Okay. And we could keep on going, so on and so on. So that's half-life and how we use radioisotopes to date all of the things in our world. Okay, cool? Okay, cool.